This is PGE334. So if you were supposed to be in EOR, it is not a class. It's in PGE 2210. But I think you are all here for geomechanics. I hope this is all of you. I'm going to count again how many students we're supposed to have in this class. But anyways, welcome again. My name is Nicolas Espinosa. I'm an associate professor here in the Petroleum Engineering department, and I've been here for already 6 years and a half, if I remember correctly, more or less. And I have taught this class for about more or less 8 times over 5 years. So during that time, I think I have managed to improve the class, so I hope you will enjoy it. Most of the material is online, and for first time I decided not to print the syllabi in paper, so everything is in Canvas. And you know, as we progress with the class, some things are going to change, not dramatically, but for example, if you tell me, oh, I don't like this date of the exam because I have this and that, or we can change that as long as you tell me in advance that you want to change. We can do that. And here, for example, we have the course schedule, what we're supposed to do this week, what we are supposed to do next week. Since we're here, let me tell you that, for example, for the laboratory number 1, it's supposed to be in the week of February 10. So this week and next week, don't worry about showing up to the lab. That's going to be, I'm going to send you a reminder, but anyways, this is the tentative date, the week of February 10. Make sure that you attend that one. But it's going to be, everything is going to be here. So I hope this is going to be useful for you to get organized. And as I was telling you, most of the material is going to be online. I have the links over here, including the notes, which is the second link over here. And these are the notes. Let me go to the front page. And these are the notes, and this is like the book that I'm going to follow. This is a summary that I have worked on for about all the time I've been teaching, but I really put together these notes about a year ago or a year and a half ago, and I've been trying to fix errors, add things in order to be consistent and to be easy to read and to be also helpful for you now for the class and also in the future. And if I come back here to the syllabus, also I'm recording, well, actually, I just remembered something. Just let me start recording this, but actually, that camera that you see over there, it's recording too, and the guy that was over here before, and this microphone that I have on, it's meant also to record the class. So actually everything was recorded by another device from the very beginning, but just to make sure that that's working all right, I'm also have my own recording system, just in case the other one fails, I have a backup. But all the lectures are going to be recorded, so I really appreciate that you come to class, so I get to know you. If you have questions, then we can discuss that. And but if sometime you cannot make it, that's fine. You make it up watching the videos. Everything is going to be there. I'm not going to penalize you by not showing up. If of course, you know, exams, everything like that, especially laboratories, you have to attend. You must be there. But for some of the lectures, if you cannot make it, that's fine. If you send me an email saying I need to go to this place and that, that's going to be even better. So I know that that you're missing for some good reason. But again, you know, I appreciate very much that you attend classes, and if you cannot make it, that's still fine. Everything is going to be here online. and it's going to be uploaded to YouTube. So it's going to be very easy for you to watch it on your computer, on your cell phone, wherever you want. If you want to look again at the lecture because there was something that you didn't understand at that time, and then you want to check it again, everything is going to be there. Okay? Good. So I think that's just one more thing about the introduction. I wanted to tell you a little bit things I do. And let's see, where am I? I don't remember where I had this. Okay, yes. So I have worked in geomechanics already for more than 10 years. And this is geomechanics. The course that we're going to look at is an introduction to geomechanics. But geomechanics is what I do research on, what I have worked with federal agencies or some companies. And here you see just a summary of things I did, just to give you a guide of things I know other than what we're going to see over here. If you at any time have any question, I'd be happy to answer those questions and help you to get more contents in depth into something that you might be interested on. Like for example on shales, I'm working on shales and conventionals. I'm working on also on carbon geological storage, and we're going to talk a little bit about this later on, and also about other sources of unconventional gas. But you know, here you have a comprehensive list, and these are most of the topics in geomechanics I work with. So I encourage you, if you have, if you want to get to know a little bit more what I do, that you take a look at this list. Okay, so let's come back to the syllabus. I like to explain very well the rules of the class, so we get all on the same page. Lectures are going to be 11 to 12:20. I'll try to respect that time, so we do not go beyond that. And as I told you, the laboratories are going, it depends on in which section you are, but are going to be at the time that you see over here. Let me zoom up a little bit. It looks a little bit small. It's going to be at those times, but it depends on which section you are, and also it depends on which week we're going to have the laboratories. We're going to have about 5 laboratories, no more than that. So just keep that in mind. It's not going to be every week a laboratory. There's just going to be 5, and I hope you'll enjoy them. We're going to have 3 exams, 2 midterm exams and a final exam. The exams are more or less cumulative, in the sense that in order to do well in exam number 2, you have to know some basic things about exam number 1. And in order to do well in exam number 3, you need to know some basics about the exam number 2 and exam number 1. Not everything, not all in detail, but you will see that there are some basic things that we're going to see over and over, that if you don't get right from the very beginning, then it's going to be difficult towards the end. But we'll talk more about exams later on, but there are going to be 3 exams, okay? And these are the dates of the exams. If you have any troubles with that, let me know in advance. If as a group you all think that we should move one of these days, then we'll do that, okay? But just let me know with enough time in advance. There is going to be one TA in this class. He's not here today because his car broke down while he was driving to campus, unfortunately. But you're going to meet him later on. He's going to help you with the laboratory and also with some of the homework. But especially for the homework, I really encourage you to talk to your fellow students and undergraduate tutors for this class, they have taken my class either the previous semester or the semester before that, and these guys are great. They're going to help you a lot with homework and with any questions that you may have. Preparing, for example, the reports for the laboratory, all of that. I'm going to tell you in advance that the homework is going to be the same as the one from last year. So here you have two options. One, you work it on your own and you learn how to do the homework on your own, and that serves as a process for you to learn as well. Or you can also copy the homework and just submit that, and probably you get the full grade for that, but you're not going to learn anything. And of course, I encourage you to do the first choice. And I'm going to give you time here in class too to work on the homework. We're going to work together on some of that homework. We're not going to have the time to do all of that, but I strongly encourage you to work on your own on the homework, because when you do that, that's going to be, you will see enough learning to do well in the exams. The exams are going to be very similar to the homework. Of course, they are not going to be the exams from last semester, right? I can guarantee that. But if you solve the homework on your own, if you read my notes, if you attend class, you'll see this class is not going to be difficult at all. But do the homework on your own. And if you need some help, here are the undergraduate tutors to help you. Out of the times, last semester this kept changing all the time. So I encourage you that you send an email to Jessica Yeager, the librarian. She's going to help you see what are the times available for this class with all the undergraduate tutors. Okay. Any questions so far? Any comment that you may have? No? Okay. So let's continue. I'm going to talk a little bit more about the contents of this class in a bit, so I'll just skip this for now. But I want to just tell you here that geomechanics is very important for your future. So you should take this class very seriously. About the textbook, as I told you again, I encourage you to follow my notes. Everything is going to be there in my notes. Actually, homework is already in my notes because are the questions for each chapter of the book. But if you want to know more about geomechanics, I also encourage you to read this book, which is a very good summary about current petroleum geomechanics, and it goes a little bit beyond what we're going to see in this class. The book is a little bit advanced and you need some prior knowledge in order to understand everything. So as we proceed with the lectures, you could read some of these chapters if you're interested in, or you could read it if you want after we finish our class. But this is a very good book. A lot of the material that I cover here is covered in depth in this book as well. And this is a very good book also to have in your library. And it's not too expensive either. So, and if you Google enough, you might find it too in a digital version. But it's a very good read. Okay, so as I was mentioning, here is the schedule, so you know in advance what we're going to see. If you want to read the notes before lecture, I think that's going to be fantastic. For example, for today, you will see that I'm not writing a lot here. It's just a very short summary. So it's going to take you just less than an hour, some of the chapters to read them entirely. So you see, usually I have very short paragraphs, and at least for this short chapter, it's about 4 pages. No more than that. Okay, so let me come back over here. And I hope all of you took petrophysics, because we're going to talk about some things that I consider more or less obvious or that you already know, like porosity, saturation, rock compressibility, things like that I assume that you already know, or sonic velocity of rock that we need here in geomechanics. If you haven't taken petrophysics, let me know, okay? But I strongly recommend that you have petrophysics already in your background. Here you have more details about the grading breakdown, and as you can see, there is a large percentage of homework. So please work on your homework. Work on it on your own. Also, you need to put some laboratory reports. I'll be talking about these later on. But this is not like petrophysics that you had to write like 10 pages, and very nicely argumented. This course doesn't have a writing flag. So what I want from here is that you summarize very concisely the results from the laboratory, and then you tell me what are the properties of this rock. If something went wrong, just say that very shortly, but that's it. I'm looking for laboratory reports that have a figure that explain what's going on, probably are not more than 3 pages long. So I'm looking for something short. And they're individual too. They are not group laboratory reports. So this is going to be your own grade. And then a 60% equally balance is going to be on the 3 exams. Okay, here's an important point. This is the tentative grading scheme for your letter grade. And usually I do not change these cutoffs. Whatever you get is what you're going to get at the end of the semester. So you can start calculating your grade and see what you're going to get. But usually, just to give you an idea more or less, I never had less than 30% of an A letter grade. So more or less, statistically, I project that at least 1/3 of you is going to get an A. Then more or less from the rest, I would say more than 1/3 is going to get something between C and B plus, and just a very small number is going to get a D or a C minus, something like that. I don't actually. I think I'm overstating this about the D's, but I think in all the time I taught, I just had like no more than 5 D's or something like that. So and in order to get a D, you really have to not attend class. You have to do very badly in exams. You don't have to show up in the laboratory. That's an extreme case. If you more or less come to class, you do your homework, you do more or less well in the exams, you're gonna get a good grade. And last semester, I had 50% A's. And I didn't change this. I'm not going to curve this to make less A's at the end, because I consider that if you do well in the exams, and if you deserve that, if you go over that number, then you're going to get that grade. All right. And as I was telling you, we have homework quite often. The homework is already there. For example, there is a homework due on Monday, but it's very easy. Don't worry. This is the first week. But then there's going to be homework almost due every week, and you have to present this almost 1 week after it is assigned. Everything is going to be on Canvas. I'm not going to ask you to do paper submissions and then you have to go into a box and then look for an hour to see what it is. Everything is going to be digital, so you do your homework and then you scan it with your cell phone, you upload it to Canvas as a PDF, and then we grade it online too. and it's back to you digitally as well. So all of that is going to be through Canvas, and I really appreciate if you, when you're in class, if you pay attention to class, that you're not on your cell phone or watching YouTube videos on your computer, except my videos, okay, that's fine, but not other videos. And again, you know, if one day you don't feel like being here because you're tired, because you went to a party, because whatever, then just stay at home and catch up later. That's fine. And don't worry about this remote attendance. We don't have remote students this time. I'm very harsh with plagiarism. So do not, I was telling you before that one option may be to copy the homework, right? But that's not really an option. If don't copy homework, because if I catch you, then I'm gonna have to report you, and then you don't want this, I don't want that either. Please do not copy any homework at all. Do it on your own, especially for exams. I don't want to catch you copying exams or copying laboratory reports or things like that, because I think I'm more or less nice, but if I feel that you know all the trust I put on you and it's not given back with the same trust, but you are cheating or you are copying something, then that's going to be not good, and then I'm going to have to report you on that. Probably I'll take that's going to have a very high penalty on your grade as well. All right, so special needs. If you have some letter with special needs, please give me that as soon as you can. For sure before the exam, okay? Sometimes I got these letters like 2 days before the exam, and then I cannot plan in advance. So if you have any of these letters, please let me know. I'll accommodate everything as necessary. And just one more thing. Remember to be very respectful to your fellow students here inside the classroom, in the laboratory, in the third floor as well, and even outside the university. And please bear in mind, I don't know if you have read this Title 9, but we should have a community that does not discriminate based on any type of profiling of people, okay? So please be respectful with all your fellow students. And I usually put this no eating during class when I was teaching at noon. So I know that's the time that before I had people, you know, bringing a whole tray of food and eating in front of me. So if you eat a snack, you know, that's fine, don't worry. But don't bring like an entire burrito here and eat that in class in front of me, because that's distracting to me, distracting also to other people. The food also may smell, and then you get distracted, right? So the idea here is not to get distracted during this hour and a half. Okay, I think that's all about the syllabus. Do you have any question about the syllabus? No? Well, if you don't have any question, then we can get started. This semester, for first time, I'm trying to go 100% digital, so I'm not going to write on paper. I used to use the dog camera before. Now, if I need to do some sketches, I'll do them on my laptop. But I'm going to try to follow as much as possible the notes that I already have in the internet. So here we are in chapter number 1, and we're going to start talking about the introduction, about petroleum geomechanics. And as you will see here, I call it energy geomechanics. All right, so geomechanics in petroleum engineering is almost everywhere. It is when you start on exploration, it's present in drilling, it's present in production, and it's also very useful when you have to get rid of some of the waste generated by our industry. So let's go one by one. How do you think geomechanics is useful in exploration? There is one example, but there are a few more. Let me zoom in a little bit more. What do we do in exploration? What are the tools in exploration? Let me go with the first one that we see over there. Structural geology is very useful. Back in the days where we didn't have all these fancy seismic surveys that we have right now, and we can see very well in the subsurface, the geologists, they were just looking at the top, whatever you see on the surface, and try to, for inference, try to see what is underneath. For example, if you had an anticline structure and you see on surface sort of an anticline, well, it's very likely that in the subsurface also there is an anticline, and it's very likely also if there is some source rock underneath that you're going to find oil on the underneath a cap rock or for such anticline. So structural geology in that sense is very useful, and rocks like an anticline. What is an anticline? It's basically rock which has been bent, has been folded with time. But how it folds, that depends on geomechanics. Another hint of what happens in the subsurface are also faults. And what are faults? Faults are basically the expression of a rock breaking in the subsurface. So here, for example, now we see with these seismic tools, we see the folding, we see the faults, and when you see that on the surface, you can interpret what is underneath. So structural geology is very important for exploration, and we're going to see it's very important too for production and for injection of waste or injection of any other fluids in the subsurface. What happens when you, for example, reactivate the fault? Anyone knows? That fault is already there. It was formed several million years ago, but with some of our operations, sometimes we can disturb equilibrium, and sometimes if we reactivate the fault, that can cause an earthquake. We don't want that to happen. So we're going to see what are all the mechanisms for that. And since we're already here, another example for geomechanics is geophysical methods. How was this seismic survey done? What is the tool that was used in order to do that? Or what is the physical mechanism that allow us to do a seismic survey? I'm sure you know, guys. What kind of what do we send to the subsurface, and what do we receive? What waves? Sound waves, right? And we're going to see more specifically that these are P waves or primary waves that depend on how stiff the rock is. And I hope also you remember from petrophysics that we have two waves. We have the P wave and the S wave, which is a compressive wave and a shear wave. And all of that also depends on the rock. What is the stiffness of the rock, how rigid it is. The more rigid it is, the higher the velocity is going to be. And all these travel times depend on those velocities. All these changes of colors, those are changes in impedance of the rock. They are showing you that there is a large variation of the stiffness from one layer to the other. That's why you have reflections, and thus those P waves bounce back to the surface because of the mechanical properties. So geomechanics is very important here, and if we take one step back, structural geology is also very important because this is actually what defines the lithosphere and the Earth's crust. I'm sure you remember from your geology class and even from high school what is the Earth like inside, right? Inside we have a very hot nucleus and a magma, and it's just at the very top that we have a very thin crust of rock. Underneath it's so hot that everything melts, but when we get to the surface where the temperature is lower, that's when many of the minerals crystallize and form rocks. Those rocks, or those thin layers, they are not continuous, and they are separated on all these plates that move. Some of them, they bounce against each other, like for example this plate against the North American plate, this Pacific plate, or the Nazca plate against the South American plate. When they bounce into each other, then you have big mountains, you have the rock breaking in compression laterally. When some of these plates, like for example here in Iceland, they diverge, all the magma comes to the surface and crystallize, coming out from, for example, from volcanoes or things like that. And those scenarios are quite different. And in between all of these plates, how the plates are bouncing into each other or extending, that's what defines what is going to be the stress inside the plate. And we're going to see that the same way that, for example, we can map in the world the elevation of the Earth, like that's what you see in colors here. The highest is brown, the lowest is green, at least onshore. The same way that you can map altitude, you can also map stress. What is the direction of stress, and also what are the magnitudes of those stresses. All these arrows that you see over here indicate what is the direction of horizontal stress caused by these plates. And for example, the direction of these horizontal stresses is what is going to tell you, we're going to see that later on, in which direction you're going to drill a wellbore for hydraulic fracturing. Because you're going to put your fracture in a way that it's aligned with the wellbore is aligned with the minimum principal stress at the given location. So, for example, wellbores here in the Permian Basin. Anyone did a internship in the Permian Basin so far? Yes. What is the direction of the wells? Horizontals. Do you remember that? Okay. We're going to see that later on. But mostly they are aligned more or less north-south, because that's the direction in this location of the minimum principal stress. And you want that, so this is north-south, right? You want that so your fractures open as planes in the same plane of here of the screen. If you put it in some other direction, your fracture is going to still go more or less this direction, so that's not going to be optimal. So I'm going to give more details about that later on. But stresses vary around the globe, and we're going to see that that's very important for geomechanics. All right, so let me come back here. We talked a little bit about completion, hydraulic fracturing. We're going to see that geomechanics is very, very important for petroleum engineering right now, especially for the USA. And before I go in detail to that, we're going to see also applications for drilling. Drilling is a very important part of petroleum engineering, and for a long time we were doing relatively shallow wells and vertical wells, but now with new methods we're extending some of these wells several miles horizontally, going into inclined directions, going into places where we never thought before. And in order to have those wellbores stable, you need very advanced geomechanical concepts and models in order to make sure that those wellbores are drilled successfully. Let me come back to completions, and just to stress the importance about geomechanics. What do you think are the top oil producers in the USA today? Can anyone tell me that? So probably you may think about the major oil companies, right? I don't know, like ExxonMobil, Chevron. Anyone has any other guess? I just remember something. I'm going to give you extra points based on class participation. So somehow, if you don't attend classes, I'm not going to penalize you, but if you do attend classes and if you participate in class, I'm going to reward you. Usually the way I do that is that let's say that you get to the end of the semester and you have an average of all your grades of 92.5. Very close to the cutoff, 93 to make it an A. If in my list I have that you have extra points, I'm going to move that to an A. So I'm going to go to the next letter grade. If I don't see any activity at all, even if you have a 92.999, that's still going to be less than an A. So I'm going to be very strict with that, but if you participate in class, that's going to help you a lot. And more or less, I think last semester I changed probably a third of the grades. I moved them one letter grade up based on this class participation. So I don't have my list today to write down if you participated or not, but I'll try to have that by Thursday. All right, so major oil producers. Any guess which are the major oil producers in the US right now? Pioneer. Why Pioneer? So what does Pioneer do? Okay.
I'm not sure.
Okay. We'll see that. I'll show you some data in a bit. Any other example? Okay. So you may be thinking about, as I was telling you before, about the major oil producers, the one that we have known for a very long time: ExxonMobil, Chevron, Shell. But the oil scenario is changing. Of course we have Chevron over there at the top, we have ExxonMobil, but look who is third. It's not that it's in the 11th place or in the 15th place, third place, EOG Resources. Anyone knows EOG Resources? So what is EOG? Where is it? Mr. What's your name? I'm looking at you with the glasses.
Angel.
Oh. Say again? Angel. Okay. So EOG, where is it located? What do they do?
I think they specialize in EOR services. Not sure.
No. Anyone else? Please.
Basic pizza, but they're very, very productive in the Eagle Ford.
Okay. Yes. So Eagle Ford, then that means shale, unconventionals, tight oil, right? So you can see that right away there in third place is EOG Resources, with almost all of its production coming from Eagle Ford and from hydraulic fracturing. And just to let you know, ESG Resources was founded by Longhorn. The CEO is Gary Thomas, and that's the person that our new building, that's the name that it's going to be called Gary Thomas Petroleum Engineering. No, it's going to be Gary Thomas Energy Resources or Energy Engineering or something like that. But he studied here like you at UT Austin. Now he has a company that is a third producer in the US. But let's just follow the list. ConocoPhillips, it also does conventional and unconventional. It has done quite a bit of unconventionals recently. Anadarko, based in Permian Basin, it's a lot of unconventional. They also have some conventional assets, but they have quite a bit of unconventionals. And now Oxy has bought Anadarko, so now they are the same thing. So actually, if we sum up those two, it looks like they might go to the very top. But why they did that? Because they saw the potential in unconventionals, and that's why they are based now mostly in unconventionals. So in the future, especially if you stay here in the US, you're going to work with unconventionals, and you're going to work with geomechanics. This course is just an introduction to geomechanics. It's just a basis, but you will see that that's going to give you a head start over other graduates that probably they didn't have geomechanics in their curriculum. I have heard from students before that this class was very useful to them when they went for internships and even when they went later for a full job. So just, I hope you get fully engaged with this class. I promise you that whatever you learn here is going to be very useful for you in the future. And this one maybe one of the topics and one of the classes that you're going to apply the most in the short term, and hopefully in the near term. As I was telling you, we're just seeing an introduction. When you get to work in the future, if you're related to unconventionals, probably you will do new things. You will elaborate new methods to make this even better. Okay. So geomechanics is very important for production. It's very important for completions. And let me continue over here. What is this? Okay. We're going to see that we're going to put a lot of emphasis on unconventionals, but also we're going to see problems related to conventionals. Like, for example, sand production. That happens when you lower the pressure so much that your rock starts to fail around the wellbore. Or reservoir compaction. Also, you lower the pressure so much that the rock is like a sponge. If you lower the pressure, if you squeeze the fluids out of it, it's going to compact. And you have some reservoirs that may be very thick, maybe relatively soft, that they compact a lot. For example, in California, there were settlements of the surface in Long Beach of up to 10 feet because of production in the reservoirs in that area in the 20s, 30s. So that's that can be quite dramatic sometimes. And we're going to also talk about the disposal of some of the waste cost. Oh, one other thing. I'm not going to give you credit for this, but if you email me and tell me, hey, there is a mistake in your notes, there is a typo, there is a numerical error, whatever, that's going to count as extra points too. Okay? So I just got a typo over here. I was telling you about waste production. As you know, when we produce oil, also we produce a lot of water. What do we do with that water? Sometimes we treat it on surface, some other times we inject in the subsurface. We have seen in the last years that injecting water in the subsurface without any control, just injecting it because we wanted to inject it without any study was not good, particularly in Oklahoma. I don't know if you remember the news about 2 years ago. There were problems in Oklahoma because of induced seismicity. Earthquakes of magnitude 4 or 5 in a region that almost never had earthquakes before. And the reason was that there were some companies that were injecting produced water into the subsurface without any control, and as I was telling you before, reactivating some faults and causing them to slip again when they were in equilibrium. We're going to see the mechanisms of how that happens and how to avoid that. And we're going to see also later on how that at a much smaller scale can also be useful for production of unconventionals. Okay, so I think I have put quite a bit of emphasis here on petroleum engineering, but I like that you keep in mind that what we're going to see, it's applicable not only to petroleum engineering but also in general to anything related to the subsurface. And for example, some of that includes the disposal of some waste produced by, for example, energy producing plants that reduce, emit carbon dioxide into atmosphere. And one of the ways of mitigating the impact of emissions into the atmosphere is to capture some of that carbon dioxide and inject it in the underground. Did you guys hear about this recent news from Microsoft that said it's going to be carbon negative by 10 years from now? So basically what they're going to do is they're going to invest in technologies that capture carbon dioxide and that store it. There are several ways to store that carbon dioxide. Sometimes you can mix it with the cement and make minerals, or you can use it for some other industrial purposes. But one of the big methods and opportunities for carbon dioxide is to inject it again into the underground. Something which is called carbon geological storage. And by doing that, it's the opposite of getting fluids out of the ground. This is injecting fluids into the ground. We could reduce the emissions of carbon dioxide significantly in the future. And you know, this was something, I've been working on this for more than 10 years, almost 15 years. And 15 years ago, I thought that it would never happen. But now I see that it's changing a lot, and there is a lot of push, not only from states, but also from private companies, as you see Microsoft over here, that they want to reduce their environmental footprint. And one of the ways is to get rid of carbon dioxide safely. And one of those includes carbon geological storage that requires our knowledge in order to do it safely, to inject it into the ground. And geomechanics is not going to be also limited to strictly oil and gas, but it's going to be also very useful for anything related to harvesting energy in the subsurface. I don't know if you knew, but hydraulic fracturing, all that research started more or less in the 80s. And it was a lot of investment from the US government trying to improve hydraulic fracturing. So in the 80s, the Department of Energy started to push this technology because they saw a lot of potential in it. And it was recently in the late 90s that hydraulic fracturing really started to get to a commercial state that it was good for business. And now we know that we can use it. It's very reliable technology, and it's changing the energy scenario. Well, there is something similar now going on with geothermal. The Department of Energy is also investing quite a bit of resources in geothermal energy, and some of this geothermal energy is called, I don't know if the project says in here, or it does say, it's called enhanced geothermal systems. I guess you all know what geothermal energy is about, right? It's just pump a cold fluid into the ground and then get a hot fluid out of the ground. And basically, you run a steam turbine on the surface or something like that to make electric energy. But what does enhance mean? Anyone could guess what enhance is in this case? Let me tell you what's the problem with current geothermal energy. Just drilling one wellbore is not enough. It's not enough surface area. Some of these rocks, which are very hot, they have a very low permeability. So it's very difficult to have a very good heat transfer because you cannot really get the fluid to flow through the rock. Everything that you get is mostly from the wellbore. So if you wanted to increase the surface area, if you wanted to have more contact of that cold water with the hot rock, what could you do? Yes, you could do directional drilling, but that's still not enough. Yes? You will be fracturing the rock, and that's what enhanced geothermal energy is about. It's making wellbores and then creating fractures that they help us to harvest more thermal energy out of the rock. Because right now, I don't have a good example out of my head, but one well is just not enough to get enough. One well it acts like as a bottleneck in the sense that you have a lot of energy, but you cannot get it out because it's just too small to get it out from there. So the same as with unconventionals, the way to increase surface area, the way to have more connection of the reservoir rock with the wellbore is to create hydraulic fractures. And that's what my friend here, Dr. Nifsi, is working on. And let's see if, I don't know if they say anything about hydraulic fracturing here, but that's what is going on, and they're doing tests in, if I remember correctly, in Idaho or somewhere over there, where they have a small, but it's not small, it's actually quite large, but they're trying this technology in a deep mine. So my message is that petroleum geomechanics, energy geomechanics is useful for producing more oil today, and it's also going to be useful in the future to produce some other sources of energy. And one more thing, also here, I like to bring this example, is that geomechanics and production from shales has been very useful for producing more oil and gas, domestic oil and gas, which is very important for the US. But there are some other benefits from it. Now, by producing gas from shales, there are many energy plants that have switched from coal to gas. And burning coal is not like burning gas. Natural gas, is just basically 99% methane, a very clean hydrocarbon. You burn it, and what do you get? You get carbon dioxide and some other small residues. But the output, the flue gas, is very clean. If you couple that with capturing carbon dioxide and injecting it into the atmosphere, the environmental footprint of that is very small. But burning coal is not the same, because coal has a lot of other things inside that burning them, they are not good. And switching from coal to gas has reduced significantly the harmful emissions of flue gas into the atmosphere, and has reduced a lot of health issues in these areas. So this may seem a little bit I don't know if you knew about this, but producing now shale from gas is actually environmentally friendly, in the sense that it is reducing a lot harmful emissions from other sources of energy, like coal. Okay. Let me see if I forget anything from here. I think we covered this. We covered that. Covered this as well. And most of what I said, it's already here, so you can read a little bit more about this. Here, let me zoom out. Here, we're going to see in geomechanics, so we're going to see almost from day one how we use geomechanics for hydraulic fracturing, and that's going to be very useful to know in which direction we drill a wellbore and what are the pressures needed to do hydraulic fracturing, and try to understand a little bit better how those hydraulic fractures forms and where they go. And you may think that all of this is already very well known, but it is not. Most people, most operators do not know very clearly where hydraulic fractures go. We have more or less an idea, and we can locate them with some tools like microseismic monitoring, but we do not have a very good idea about if we have 1 fracture, 2 fractures, 3 fractures, or 10 fractures, because that's very difficult to see in the subsurface. And currently at this time I'm working in a project that has as an objective try to understand that better, and next to a hydraulic fracturing job in this project there is a well that has been drilled and goes close to that completed area, and we have retrieved core from that well in order to see if we actually see fractures or not. And some of those results are very eye-opening. Many of the models that we have, conceptual ideas that we have about hydraulic fracturing, they are not true. And in general, you tend to see more fractures than what you may think with simple models. Okay, so let's see if I forget anything over here. We talk about reservoir geomechanics, compaction, subsidence. In unconventionals, some of these problems of compaction, they can be very bad, in the sense that you can break some of your casing, adding too much compression in a formation, or if, for example, you reactivate a fault, like in this case over here, you might shear your casing because imagine that one part of here the subsurface stays where it is and the other one moves. That's going to cut the casing like nothing. It's going to be very, very easy. And if you had some other reservoir going over there that you were producing and you reactivate the fault, you're going to cut your casing, you're going to cut your producing tubing, and that's not going to be good at all. All right, and then we get to the end of this chapter, and this is the homework that I want you to work with for next week. So I told you 1 week in order to solve the homework. This is very short, and it's going to be due on Tuesday next week. And basically what I want you to do is to read these 2 reports from the International Energy Agency, where they show the trends of production of shale gas and tight oil in the U.S. And I want you to see, just get an idea with numbers about how much that has grown in the past and what has been the impact in the U.S. economy and in the petroleum industry. So just let's pick one of those reports. I'm going to check also if the links, they work. So it's a relatively long article, but it's not that long. What I want you to look at in detail are some of the figures in here that are not loading for some reason. So wait a minute. Okay, we have some of the images here. Okay, let me look in detail. Okay, I think this was one of the graphs I wanted you to look at. Here you have a plot of gas production in the US according to the source, where here you can see how this light blue increases. This is shale gas from the Permian. In the 2013 there was almost nothing. Now it is 15-20% of total production in the US. In dark blue you have shale gas from the Appalachian Basin, mostly Marcellus. And then you see also that now it's 35-40% of the current production. Well, okay, this is a prediction, 2023. Probably you should look over here, 2019. But what I want you to do here is just to see how much it has grown and what is the importance, especially of geomechanics for unconventionals, for shale gas and for tight oil. And let's see if figures, they didn't load over here, but let's try this way. You might have to register, but I'm pretty sure this is going to work on your computer. It might be a problem with the Zoom or something like that. Okay, well, if it doesn't work, just let me know. But similar to the other one, there should be some figures over here that I want you to look at. And so there is one question about the gas, one question about the oil, and that's it. So I think we're close to the end, and we still have more or less 15 minutes, but I'd like to finish this introduction here, and we'll start talking on Thursday about how to calculate pressure and vertical stress in the subsurface. All right? Okay. I'll see you on Thursday. Thank you, guys.